Ready to go then? Okay.
Yeah.
Well, it's great to be back, and impact craters are really fascinating. They're neat for a bunch of reasons. They're marvelous to go and visit, and in some cases they're in exotic, neat places like the Arctic. I went to some pictures. Africa. I went to the Subtweed crater in Ghana. Places like that. So some neat things, but in the context of Mars and planetary exploration, they're really important. Just starting. So, in many cases, you could argue that they are the most important surface process on most of the solid planets. The Earth is kind of an exception, but we do have impact craters, and I have a big piece of an impact crater from the Santa Fe structure that was discovered recently that we're working on. So evidence of cratering is preserved on almost all the bodies of the solar system except for the large gas giant planets. The impacts affected the evolution of life on the Earth. We'll talk a little bit about the Chicxulub KT boundary impact. And there's a good chance that an impact was responsible for the origin of the moon, could have been responsible for the loss of Mercury's, a bunch of Mercury's mantle, and other huge effects across the solar system. So let's see, is this advanced? Oh, excellent. Okay. So this is probably the most famous crater, and this was important historically for a bunch of reasons. In particular, this was the first impact crater that was really proven, and so it's very important. Notice it's a simple bowl-shaped crater, and and simple is the defining word here. We'll talk about that. Actually, there's a funny story here. Over here is the visitor center, and one of my former directors said he was giving a talk, and someone asked what this was, and they said, "Oh, that's the visitor center." And the person said, "Wow, that giant crater formed and didn't even disturb the building." Didn't quite get the concept here. Deer crossing. So we're going to talk about some basic concepts. So I mentioned the idea of a simple crater, simple impact crater. There are craters up to about 10 kilometers or 5 or 6 miles in diameter. It varies a little bit depending on which planet you're on. Notice this is very similar in some ways to meteor crater. It has a nice ejecta blanket. This is from Mars. And so this is the cross-section of a simple crater. You have the ejecta blanket outside, you have the crater rim, you have a depth and a diameter, and you can have, in the floor of the crater, you can have breccias. These are broken up rocks. And then under the crater floor, the rocks can be broken and shattered, and there's possibilities of other things like shatter cones underneath. There's no central uplift in this example here, and that's part of what makes it simple. You go to the next type of crater. This is a much bigger crater. This is a 40-kilometer diameter crater. Anybody have an idea what planet this might be on? Mercury. Any other ideas? It's actually Venus. So, and this is a radar image. So it's kind of interesting. You can see that the ejecta from this is very extensive, probably due to the high temperatures of the rocks in the impact hit. A lot of melting. Okay. And what planet? These are two craters. They're about 36 and 26 kilometers in diameter. Why would you think it's the Earth? Yes. This is actually the Clearwater craters in Canada. And the blue stuff is water. They've been made into a reservoir. It's actually been dammed up, and the lakes are deeper than they were originally. So, so these are
located?
in Canada.
Which province?
It's in northern Canada, so in the northeastern Canada. There's a possibility. We think that the moon formed when very early in the history of solar system, when a large one of the large protoplanets hit the Earth, material was ejected that then coalesced to form the moon. And so then we can talk about the sources of impacting materials. There's two main sources for the kind of craters that we're going to be talking about now, more recent ones. And that's the asteroid belt, which is between Mars and Jupiter. It's where most of the craters are located. And then much further out from that is the Oort cloud and the Oort cloud and the Kuiper belt, which sends comets in to the Earth. And so here are some asteroids, and this is a very big asteroid, Ida, and this is its little tiny satellite Dactyl. We now know that there are a lot of these small asteroids that are actually have their own satellites, which is kind of neat. And you can see that Dactyl even has been hit as well, and there's craters on it. If this hit the, this is big enough to cause major disruptions on the Earth. Yes?
I just wanted to ask, do we know whether Dactyl actually orbits Ida?
Yes.
Or does it travel with it?
It orbits it. Yeah. And we've now, it's something like 20% of asteroids have satellites. It's really interesting. But then there's also comets. And here's a couple of our comet pictures. And very exciting. Coming up next year, we're actually going to land the Philae lander on Europe's mission. The Rosetta mission will actually come down with legs and land on a comet. Okay, there are smaller craters. This one is a little bit bigger than Meteor Crater. This is the Lonar Crater in India, which I've been studying. It's a pretty neat one. This is important because it's emplaced in basalts, and so you can see the layers over here, and so it makes it a lot like Mars, and so that's kind of neat. Although our current crater is not emplaced in the Gale crater that Curiosity is in is not in basalt, but it's in the crust. But much of Mars and the Moon are covered with basalt, so this is an important crater for planetary science. There are other bigger craters. This is Manicouagan. Huge crater, also made into a reservoir. So now we can talk a little bit more about some of the features that go on during cratering. There's a ton of information online, a lot of different places, including at LPI, about impacts. But just to talk a little bit about what happens in a somewhat bigger crater. You have a projectile coming in, and on the Earth they hit about 20 to 25,000 miles an hour, 10 kilometers per second. When they hit the ground, what happens is you set up a shock wave, and the shock wave propagates outward and back into the projectile. And there's so much energy involved that close in, you actually melt the rock. And so you get what's called impact melt. And then further out, you shatter a whole bunch of rock here. This will be thrown out and land and form the ejecta blanket surrounding the crater after a short amount of time. And then further out, you get these fractured rocks, and this is where you can have shatter cones. Now, shatter cones are rocks that have been shocked. This is a cool example from Santa Fe, from the Santa Fe impact structure. And that one's highly eroded. This is probably from below the crater. So we can come up and take a look at that later. So the shock wave goes flying outwards. There's another neat thing that happens, and that is the shock wave can come up and to the surface, and so you've got the shock wave rippling through. It hits hits, you know, the rocks, and those get accelerated. Those rocks hit the next rocks, and those rocks hit the next rocks. And then at the surface, the shock wave hits those rocks, they're accelerated, but there's nothing to stop them, and they fly off. And this is one of the main ideas about how we get meteorites from the moon and Mars, is this idea of spallation. Okay. Well, craters are fun. This is me at, up at the Houghton crater in Canada. And the scenery is completely amazing. And NASA helped support a Mars research station up there. And look what is present there in a good, one of the early strong indications of impact, that you actually have an impact crater, was the discovery of these shatter cones. So this is a shatter cone. Here's a pen. So you can see this is a pretty big sample, even bigger than the one I brought in from Santa Fe. Okay, now there are some cool craters that I had hoped maybe we could get out and see, but it's too cloudy today. But you can ask your students, have you ever seen an impact crater? And then if they say no, well, you can say, have you ever been out and looked at the moon? Because some of the biggest impact craters in the solar system are visible to our naked eye just by walking outside and looking up at the moon. And so you can see Mare Imbrium, and through a small telescope, it's easy to see Tycho and its rays. So it's actually pretty neat that we can see these huge features. And it's another indication of how important they are in the solar system. So when an object first hits, material starts spraying out due to the impact. So you get this high-speed jetting, and this can affect the atmosphere. But more important is that material starts getting thrown out, and it forms this ejecta curtain. This is material flying out that's going to land back on the ground and form this ejecta blanket that's easy to study in relatively fresh craters. Okay, now we have to talk about the other kind of crater. When you get to bigger craters, bigger than, say, 10 kilometers in diameter, say 5 miles or so, the effects of gravity on the bowl that's formed, what we call the transient cavity, gravity starts to become much more important. And what you do is you get collapse. The walls collapse back down. And so here what happens is you start to form this excavation. The ejecta is flying outwards. And two things happen. The walls are collapsing back down again, and you also get rebound. You've pushed down the rock in the center, and it comes back up. And this can be really very drastic. You can have kilometers of uplift. You can have a mile uplift. And this is one way they recognize them, impact craters in sediments, places like Kansas and that sort of thing. They'll in the seismic lines, they'll notice, oh, why is there this big rise in the bedrock underneath? And so they've identified buried impact craters, and actually many of them in sedimentary basins. Because why do people study sedimentary basins with seismic studies? Oil. So, we can't afford to do seismic studies, but the oil companies definitely can. So we have two classes of craters. The two main classes are simple craters and complex craters. The complex craters, like Copernicus on the moon, have a central uplift, and then they have these terraces due to collapse of the crater walls. Okay, then at the late stage, material keeps falling out. This can lead to other deposits of other materials, a material called lapilli, other interesting things you might read about. So this stage and the formation of the ejecta blanket is very much like a volcanic eruption. You have this big cloud that goes up, and then the material falls back out. While material's up high in the sky, it's hot in a volcanic eruption. It can stick together and form these little lapillae. You can have melting. This stuff falls back out again. And so it can be very hard to tell apart a volcanic eruption from an impact. And so, for example, the Ries crater in Germany we'll get to, for decades people thought it was probably a volcano because the deposits look just like nearby deposits from the Eifel volcanic region. And so it wasn't until the 60s that they started making the connection with impacts. So, so this is the classification of craters. Here's meteor crater, a simple, still basically a bowl-shaped crater, and then vastly larger complex crater. Simple craters, again, are bowl-shaped. One thing that can happen is the ejecta, you can actually almost turn it back over like a flap here, but these tend to be all broken up. So you get what's called inverted stratigraphy. The stuff lying up here can, at this classic meteor crater occurrence, it's sort of turned inside out a little bit. And another characteristic, you can see it's kind of hummocky in here. So that's another characteristic of an ejecta blanket. And then down in the crater floor is a lens of breccia. Again, breccia is broken up rock. I have an example of ejecta from the Ries crater that includes impact melts here, and you can see that there's fragments of broken rock in here. Now, meteor crater, the other thing that that happens, and I've got some samples here. This is sort of more typical of the sandstone, but this is some of the sandstone that experienced a lot of the shock, and it's actually been turned into a sandstone pumice, a silica pumice, which is pretty interesting, and you can tell how light it is. So there's different kinds of shock effects. You get the melting, you get shatter cones, and it doesn't take a huge amount of shock. You can get the formation of this kind of pumice, and then as you get to much higher levels of shock, you get melting. And I'll show you some other examples of that. Well, the other thing that happens is something I've studied, which is hydrothermal processes. So in large craters bigger than a few miles across, you have so much hot rock that if you have any water around, like groundwater flowing in, that water, you end up with hot water. And hot water and hot springs, may have been connected with the origin of life. That's why people study Yellowstone, for example. And so there's a couple of ways you can get on Mars, if you're looking for evidence of hydrothermal, you can get it, of course, from volcanoes, but those rocks can be deeply buried. But the impact craters may reveal this kind of material. So there's more than one kind of heat source. You get the heat from the impact melt. And then I was talking about how the rocks are lifted up in the center. Well, rocks that are deeper down in the Earth and other planets are hotter. And when you bring that up, it creates a heat source. And so you can get hot water circulating around. And this is the sort of thing that the astrobiologists are really interested in trying to find. And so we're also looking for evidence of this geochemically, for example, in Gale Crater. Okay. On the Earth, there's this concept of life in extreme environments. These are black smokers. This is from the heat from the formation of the mid-ocean ridges, and then Yellowstone hot springs, also volcanic sources of heat. And there's a thought that this potentially connected with the origin of life. We do find these in Martian meteorites. This is alteration material in the Lafayette Martian meteorite. This is very tiny, 1/10 of a millimeter. So this is an image from a microscope. But at Lonar Crater, we've also seen things. This is a When I first arrived at the crater, India is an amazing place. These women were bringing firewood up out of the crater. And a week later, I was I was staying at a research facility in India, and a meeting was going on. I wasn't involved with it, but the meeting was on quantum cosmology. So here you have a country where you have women bringing out the firewood, and in another part of the country they're talking about quantum cosmology. So we live in a really kind of an amazing time period in human history. We can be doing this. So here's Lonar again, and there are drill holes down through here, and we have found evidence for some hydrothermal processes in samples from below the crater. I'm not going to go into that. I mentioned the impact melts. Here's some impact melts at Lonar crater actually sitting in situ in the ejecta blanket, and I brought a small piece of one for you to look at. If you look at it, you'll say, wow, I couldn't tell if that was volcanic or not, and that's correct. It's not so easy to tell. Okay. In the ejecta blanket, there's big pieces of rock that were thrown out. Here's some other examples. So it's pretty neat. Now we're going to go back to the bigger complex craters. And so this is very schematic, but some of the components, they're a little more complicated in these much bigger craters. And so this idea of a transient cavity, when you first form the crater, you have this big bowl-shaped feature. But in these large craters, this is so huge that the rocks can't stand up, so they start collapsing back down along faults. And you end up getting the rock moving, and then you end up with these terraces. And then you also get the rebound coming up from the center to form central uplifts. So this is for much bigger craters. So you get these terrace faults. You get breccias, and then you get an impact melt sheet. So they're a little more complicated. So the Ries crater in Germany, this is a really amazing place to go. Among other things, it's on the Romantic Road, and the cathedral here in Nördling, town of Nördlingen, is built out of this stuff. This, which is the impact melt rock created by the crater. So one of my colleagues said this was the most cosmic church in Christendom. So you can go and visit that. And so that's pretty neat. And the town of Nördlingen is really amazing. It's a medieval walled city. It's just north of Munich. And like I said, it's on the Romantic Road. So you can combine a fantastic trip through central Germany with that. So this is, yes. So here's another picture of the crater. And this is a cross section. This is without vertical exaggeration. And so you can see that in a large crater like this, it's actually very, very flat, very shallow. The crater floor is covered with farmland because it was a lake and then filled in with sediments. But this is schematically based on seismic data. The rocks beneath the crater are shattered and a little bit lower in density. And then, so it's a neat place. Here's an outcrop of the Suevite, and there's degassing pipes. This is actually where gases have escaped upwards. This is from the same location. Some other examples, and you can see the fractured rock, which is why it's called a breccia, and these are fragments of impact melt. So I'm just going to go on. Now, impact crater energies can vary over a phenomenal range, an absolutely amazing range. And just as a quick idea of what of the ranges, you can go up to you can look at the, this is joules down here, or megatons of TNT equivalent. And so as you go up in energy from small craters, meteor crater, it's conceivable we could make something like meteor crater with nuclear weapons. But all the world's nuclear arsenal, and this is probably 10 years old, we've now gotten rid of most of those, but there's a lot fewer, fortunately, nuclear weapons, falls down in here. And you get up to these large impacts like Manicouagan in Canada, or the Chicxulub crater at the KT boundary that killed off the dinosaurs. And you are millions of times more energy. So absolutely phenomenal energy. Still not enough energy to affect the rotation of the Earth or anything like that, but a lot of energy. I'm going to go through this real quickly, but it was pretty neat. This is Carolyn Shoemaker, and they, we understand more about what happens with impacts. And this was comet Shoemaker-Levy. It was discovered in 1993. And then Hubble took some pictures and showed that there was a whole train of comets. And they figured out that this comet had passed by Jupiter, and Jupiter's gravity had disrupted the comet, and then it impacted Jupiter. If these fragments had hit the Earth, we wouldn't be here talking. Pretty amazing. But they were able to see the effects on Jupiter, including the effects of disruption of the atmosphere. Now, for the implications, some of the implications for the Earth, impacts on the Earth will punch a hole in the atmosphere, and we think that happens on Mars too. And you can get plumes just like the one seen on Jupiter. And there's features like the Tunguska that may have been due to a broken up comet that happened in 1908. So these are, we're certainly can be affected on the Earth. And we had the recent event in Russia as well, as an example. So the other big deal for impacts on the Earth is this Cretaceous Tertiary Boundary event, which is recorded in New Mexico, and we'll can learn a bit more about that at the Natural History Museum. But about the discovery of this was due to these guys here, and Walter Alvarez and his father, who was Louis Alvarez, who was a Nobel Prize winner. They wanted to do some work together, and Walter is a stratigrapher, and he was working in Italy, and they were trying to figure out how long the breaks were between these geologic eras. And they had the idea that, there's cosmic debris raining down, and so if you could measure that, it would act kind of like a clock. If you see more of it, that means a longer time period. So they measured it, and they found this big enrichment in iridium, much too big to explain by just time alone. And then they did some more work, and it was discovered that this occurs all over the world. So here's the concentration of iridium versus the depth in this. This happens to be in a New Zealand section. And the abundance of this element iridium, which they could measure up at Lawrence Livermore Labs, was way higher in this boundary clay. And that was the first evidence that a major event had occurred at this time, which was when the dinosaurs disappeared from the Earth. People then studied these sections all over the world. This is a section from the Raton Basin in northern New Mexico, and we collected a piece of that. And so with another couple of years study, it was realized that this Chicxulub impact crater formed about 65 million years ago, and it was such a big event that it sent ejecta that landed in different parts of the world, including up here in New Mexico. And so pretty interesting. There's seismic evidence for this, and then we have drill holes, and in these KT boundary materials, there's evidence for melted glass spherules, again, other evidence for impact, and then shock effects in quartz. So pretty neat. And we've actually drilled holes down into the Chicxulub impact crater, and here's one of the drill cores. And what you can see when you look at this is that this is also a breccia, and this is part of the ejecta. So it has a lot in common with this ejecta from the Reese crater. So you can take a look at that. So it's pretty neat. And so we've done, we've documented a lot of evidence for these hydrothermal alteration of that material from the Chicxulub impact crater. So Chicxulub is a complex crater. Here's a bigger picture of the drill core and a drill rig. And then, so it's a complex crater too. This is roughly the area where we drilled. This is highly schematic, however. Okay. So before we switch to Mars, are there any questions about this so far? And I'm not sure. How long were we going to go?
Till 10:30, we'd like about 10 minutes.
Yeah. Okay, good. Well, then I'll have time to talk a little about what we're seeing from Curiosity. But yes.
I just had one quick question near the end of that. What's the significance of iridium? Sorry, I wasn't.
Okay, the iridium is just a tracer. It's rare in the Earth in terrestrial materials because it's down. It likes metal and it's down in the Earth's core.
Oh,
But meteorites have iridium in them at higher concentrations. So you can measure the amount of influx of material by measuring the iridium. So it's just a bit of a tracer. Yes.
Are there places around here where you can see them?
Up in northern New Mexico, up near Raton Basin, there's a number of localities. In fact, there's a city park where there's big signs where you can go and see that. So that was it was an inland sea at the time. Yes?
Can you tell anywhere where the people go?
I've been there, and it's a pretty neat. I think the evidence for it being an impact is pretty good, but it's pretty highly eroded, and it was emplaced in sedimentary rock, which makes it harder to retain the evidence for it being an impact. But it's been studied pretty extensively, and I think it is a pretty good impact is the most likely explanation. Yeah.
When you're showing the schematic, the crater in India, it said crater floor temples. Are those geologic features or actual temples? Or?
Those are actual temples. Yeah, I mean, one of the neat things about visiting India, and one of the things that makes it a little more complicated, is the thousands of years of human occupation. So when we're looking for impact melts, you have to be careful not to pick up primitive bricks that have been also where they took the mud and heated them up and all that. So that when you're in an area that's had 1,000 years of human history, you have to be a little careful of stuff that you just pick up lying around where it actually came from. Something that's easier in other parts of the world. So yeah, so Lonar is a neat place to visit. There's some other, not too far away, historic areas, and it's a national park. The county of that Lonar's located in, they actually have a tourist hotel there, which is quite reasonable, and so going to India and going to rural India is a trip, but it's doable if you want to do that. Yes.
And on one of the graphs, you had a number of families on axis, families of.
Right. That was just to reflect the the fact that throughout Earth's history, since there have been organisms up to about 500 million years ago, that we can see these episodes of mass extinctions in the history of life on the Earth. The KT boundary, or at 65 million years, when the dinosaurs were killed off, that's probably the best established that an impact was responsible. There is a chance that some of these other boundaries, there are tectonic events or volcanic events, could also be responsible. That raises an interesting thing. One of the things that, and this is a kind of a neat story about how science works. When it was first proposed that there was an impact that killed off the dinosaurs, a lot of paleontologists were really kind of upset by this, and they didn't like this idea because for hundreds of years they had assumed it was volcanic or other environmental things. And furthermore, but the interesting thing is that even Darwin was aware of these mass extinctions. This was known. He had to kind of sweep this under the rug to talk about evolution as a constant thing. But so when they came up with this idea, okay, we've got this idea that maybe something killed off the dinosaurs abruptly, right at this boundary. Well, how do you show that with the fossils? Okay, well, very easy, right? Here's the Cretaceous rocks, and you look for fossils of dinosaurs. Well, there's a fossil here, and a fossil here, and a fossil here, and a fossil here, and one here, and one here, and one here. Well, as you get closer and closer to this boundary, there's less and less fossils. Well, it turns out that the paleontologists did not bother to record where